So there are many ways of describing sequential circuits, and we're going to talk about all the different ways to describe them. We already looked at the NOR SR latch, where you have the cross-coupled NOR gates, inputs S and R, and outputs Q and Q naught. We had looked at the form where we just have the output Q, but this shows the output Q and Q naught. We drew a truth table for this gate with SR and Q as the inputs and Q next state as the output. And we noticed the hold condition was when S and R were both 0. The reset condition was when S was 0 and R was 1. The set condition was when S was 1 and R is 0. And the forbidden condition was when they were both 1. And this is because in this cross-coupled form, having both conditions being 1 would cause both Q and Q naught to be the same value, which is not valid. So this truth table here is known as a present state next state, or PSNS table. And the reason why it's called that is because it tells you the present state Q and the next state Q naught. So instead of calling just a basic truth table, we call it a PSNS table. Then we looked at a compressed PSNS table form where we had noted that 0, 0 was just Q, 0, 1 was 0, 1, 0 was 1, and 1, 1 was X, or forbidden. Okay, now you can actually rearrange this table into another form called an excitation table. And in the excitation table, you show your present state Q and your next state Q plus, and show what conditions would get you from Q to Q plus. So in this case, let's say you were in state 0 and you wanted to go to state 0 again. Well, if we look at our PSNS table, we're in state 0 and want to go to state 0 again. We could have the condition where S and R are both 0, which is this first row in the truth table. Or we could have the condition when S is 0 and R is 1. Or that's all. No other condition brings us from 0 to 0. So you can see in this case, it's when S is 0 and it doesn't matter what R is. So going from 0 to 0, S has to be 0 and it doesn't matter what R is to go from 0 to 0. Now if we were in state 0 and wanted to go to state 1, what do our conditions need to be? Well, if we're in state 0 and need to go to state 1, that's over here. That's a set condition when S is 1 and R is 0. And that's the only condition that does that. So, if you look at the excitation table, the second row is when S is 1 and R is 0. Now, if we want to go from state 1 to state 0, we look again in our truth table or present state next state table, and we go from 1 to 0 when S is 0 and R is 1. And that is the only case, going from 1 to 0. So there you go, when S is 0 and R is 1. And if we want to go from 1 to 1, we have this row when S is 0 and R is 0, and also when S is 1 and R is 0. So again, R can be 0 in both cases, and S can be either a 1 or a 0. So S is a don't care, and R is a 0. So we've just described all the state transitions, going from state 0 to itself again, from state 0 to 1, from state 1 to state 0, and from state 1 to 1. Now this is really important to know how you get from one place to another place with certain input conditions. It's a really good way of describing that. Alright, so we can also model this sequential circuit with a lovely black box diagram. So we have inputs S and R, our output Q, our present state, and Q naught, which is modeling this form of the circuit. And then we also have our state diagram, and the state diagram is just another way of describing this excitation table. So we have the state where Q equals 0, and to stay in that state, Q equals 0, we have to have S being 0. So we draw our line to stay in the state, and describe what input conditions cause us to stay in that state. So it's when S is 0, which corresponds to this row of the excitation table. It doesn't matter what R is, so we don't have to put R there. Now if we want to go from 0 to 1, which is the second row in the truth table, that's when S is 1 and R is 0. So we can write our transition, our state transition, which is this arrow here, to go from state 0 to state 1. It's when S is 1 and R is 0. So we write it as SR naught. So as you can see in the state diagram, you write your states in bubbles, and you write your transitions as arrows drawn between the bubbles, and label the arrows with the input conditions that cause those transitions. So you can see now going from state 1 to 0 is this arrow, and it's when S is 0 and R is 1, so S naught R. And then when you go from 1 to 1, you stay in state 1, it's when R is 0. So it's very important to know all these forms of modeling sequential circuits. And we will be going through some more examples of using all these types of tables as we talk more about sequential circuits.